of growth. We just talked about some important ingredients to allow life to grow. So now we'll talk about the patterns we see in terms of growth with microbes in particular, but some of this is applicable across life forms. So when we're talking about microbes in a petri dish, this is the growth pattern that you typically see. So there's 4 phases here. There's lag phase, log phase, which is sometimes called exponential phase, stationary phase, and death phase, which is also sometimes called decline phase. So lag phase, there's 2 reasons for it. One reason is when you plate a microbe, you've had a microbe from an environmental sample that was living in the soil or that was living in a human body or that was living in the ocean, and now you're putting it in a petri dish. It sometimes takes the microbe a little time to get used to the new environment, so it needs some time to switch on the right genes to survive in that particular environment because it's just had a big change. And that can be one reason you get this lag, this very, very slow growth rate or a lack of growth at first. But mostly lag phase and log phase or exponential phase are actually part of the same pattern. So they're just part of what is known as exponential growth. Exponential growth is when you have a constant doubling time. So it doesn't matter if the doubling time is an hour or a day or 70 years, as long as it's always the same, it's unchanging. And what I mean by doubling time is it takes that amount of time for the population to double in numbers. So if the doubling time is an hour, that means every hour you have double the population of the previous hour. So 1 doubles to 2, 2 doubles to 4, 4 doubles to 8, 8 to 16 to 32, so on and so forth. And so whether that's an hour, a minute, a year, it doesn't matter as long as the time it takes to double is unchanging. It's always the same amount of time that it takes to double. So when you have a constant doubling time, you get this pattern of growth, which is encompassed by both what we see called here as the lag phase and the exponential phase. They're actually part of the same thing. Because when you have a constant doubling time, when you have exponential growth, you get slow growth at first, and then growth starts to speed up, speed up, speed up, speed up, and you get this upshoot eventually. And the reason is, you're starting out by doubling small numbers. And when you double a small number, you get another small number. But eventually the numbers, they're getting bigger, but they're getting bigger very slowly at first. But when you double 1, you get 2. 1 is a small number, 2 is a small number. Double 2, you get 4. 2 is a small number, and 4 is a small number. So you double a small number, you keep getting small numbers. But at some point, as you follow that pattern forwards, you're doubling 1,000 to get 2,000. And then if you keep going further, you're doubling 1,000,000 to get 2,000,000. So you can see that you're not just adding, when you're adding at a consistent rate, you're always adding the same amount. Whether it's a large number or a small number, it's always the same. But with exponential growth, you're doubling, which means at first you're adding on small numbers, but the numbers because you're not actually adding, you're multiplying, the numbers getting added with each doubling time are larger and larger and larger and larger. So growth actually gets faster and faster and faster. The doubling time isn't changing. You're still doubling the population at the same intervals as you were in the beginning, but the number that you're doubling is a larger number at the end than it was at the beginning. So let's look at this more closely. So here, I put the numbers on the side so you can sort of see how the math works, but if that makes you crazy, then you don't even have to look at it. You just have to get this idea that, okay, here is just some made-up bacteria with a fairly, with some doubling time. And all I've said is number of generations. Every generation could be a minute, every generation could be an hour, every generation could be a day, it could be 2 days, it doesn't matter. So let's just say it's a day. So let's say this is a bacteria whose numbers double once a day, okay? So that's kind of slow growth actually for bacteria. So every, so this is 1 day, this is 2 days, this is 3 days, this is 4 days, okay? And let's just say you started with 1 bacteria. So total cells you start with are 1. So double 1, you have 2 the next day. Then you have 4, then you have 8, then you have 16, 32, 64, and so on. But you can see this pattern like we saw in the beginning, because by the end you have 512. So you can see that even though we only have 512 at the end, you're already starting to see this pattern where the growth looks really slow at the beginning and faster at the end. Nothing has changed. The doubling, the way that bacteria double is through binary fission. And so that means 1 cell divides into 2. And we're saying that this is a species that does that once a day. So 1 cell doubles into 2. If you have 2 cells, each of those are also going to go through binary fission once a day to make 4 by the next day. Every single one of those 4 is going to go through binary fission by the end of the following day. That's going to make 8. So their rate of growth, the rate at which they copy themselves is not changing. They're not copying themselves faster and faster. What's happening is that there are more and more cells to copy themselves towards the end of this graph relative to the beginning. At the beginning, you had only 1 cell copying itself. By the end, you have 512 to copy themselves. So obviously, if you're doubling 512, you're going to get a much bigger number than if you're doubling 1. So this is just the consequences of exponential growth, and we see this is very common for populations everywhere. All species follow this pattern at some point, because we don't usually change our doubling time. Whatever individuals are there, it usually takes them a certain amount of time to reach reproductive maturity, and then they have offspring, right? And they double their numbers. And it's usually the same amount of, it's not the same for all species, but within a species, the rate at which the organisms copy themselves doesn't change over time. So for humans right now, our doubling time is every 70 years. So if we have 7.5 billion people on the planet now, then we're going to have 15 billion people on the planet in 70 years if our doubling time didn't change, right? And it's been the same for, since the Industrial Revolution. So what are the consequences of exponential growth? So this can be really hard for people to think about because we're used to straight line growth. That's how we think. We think linearly. Instead of thinking about doubling and the consequences of doubling forever, we usually think about the consequences of adding, not multiplying, but adding forever. So we think of our growth in a straight line, and it's really difficult for us to imagine the consequences of exponential growth, which are extraordinarily slow growth initially, and then this skyrocketing of growth at the end. So to help visualize this, I have this little myth that I think really exemplifies the math really well. So there's this story about the man who invented the chess game. And the king was so pleased with chess, with the game, that he offered this man whatever he wanted. And the man was a mathematician. So he put a single grain of wheat on the first square of the chessboard. And he said, in each square, I would like double the wheat in the previous square. So that means that in the next square, he wanted double 1, which is 2 grains of wheat. For the square after that, that would be 4 grains of wheat. Double 4, the next square would be 8 grains of wheat, so on and so forth. And the king thought, what a silly request. This man could have anything he wanted in the entire kingdom, and all he asked for was a handful of wheat. But how much wheat does this turn out to be? Well, there are 64 squares in a chessboard. So if you keep up this pattern for 64 times, you double the previous square 64 times, by the end of the chessboard, you have over 18 quintillion grains of wheat, which might be more wheat than even exists in the world today. So populations that experience what we call constant growth, a constant growth rate, pose special problems to graphing. How can you possibly make a graph that accurately displays what is going on in the early phases of growth at the top of this chessboard, but also shows values large enough to show what is going on in the later phases of growth, lower on the chessboard? This graph shows E. coli growth over time and is scaled to display up to 18 million cells. In this E. coli population, cells divide every hour, which means the population doubles every hour. And that is pretty typical for bacteria. They tend to make a new generation, the next generation, fairly rapidly. So doubling every hour is pretty typical for bacteria. Because growth starts slow, it is very hard to see. I mean, it's not that it starts slow, right? I mean, that's kind of a misnomer because their doubling time doesn't change. They double in numbers every hour. But the number of cells that you're adding each hour or that you're multiplying each hour are very small at the beginning of this graph. Oops. So you really can't see what's going on before the 13th hour. From the 13th hour earlier, it kind of looks like you have 0 cells, which is not at all true. There are many more than 0 cells for the first part of this day, because this is a 24-hour cycle, right? So the first half of the day, it looks like there's 0 cells on this graph, and that's just not true. It's just that the numbers are too small to see, given that this graph is scaled to see 18 million cells at the end of the graph, because when the numbers that you're doubling start to get really large, and growth skyrockets at the end of this graph here. So it's scaled out so you can see that large growth at the end, but that obscures the growth that's going on at the beginning. Additionally, a problem with this graph, this is the way we normally graph things, right? This is a typical graph. Another problem with this is, let's say you wanted to collect one more hour of data. So, you have 24 hours of data here. There's an empty slot for the 25th hour. What would you have to do? Well, the population doubles every hour. So you have 18 million cells at the 24th hour. To add a data point for the 25th hour, you can expect that you'll have to double 18 million. So you'll have 36 million cells. That means you're going to have to double the height of this graph, right? And if you don't double the height of the graph, you're going to have to scale out again, so that you're going to obscure even more hours on the early phases of the graph, so that you won't be able to see how much growth is going on earlier. And then again, what if you wanted to add 2 more hours of data? What if you wanted to add a whole day's worth of data? Well, you're just going to have to scale out so much that you're not going to be able to see anything that's going on in the first day, pretty much, of growth. So what we do is, in order to adequately see the early phases of growth, and also to make it more convenient to add new data points as data collection continues, we use what's called a log scale graph. And I want to point out some differences. I know that this looks different, right? Because this is the exact same data. You're not changing the data. The cell growth numbers, the cell numbers are what they are. So you're not changing the data. All that you're doing is changing how you're displaying the data. And I want to really make that clear, because I feel like in the homework that follows this lecture, one of the things students really get confused about is they think that they're supposed to manipulate the cell numbers. No, the cell numbers don't change. The data is the data, and it remains unchanged. All that you're doing is you're changing how you show the data to make it more clear. So you can see that in this is called a log base 10 graph, and I'll explain what that means in a moment. But one thing I want to point out is it straightens out this line. So one thing that students, and a lot of people really don't like about these graphs is it doesn't make it intuitive, the pattern of growth. When you're looking at a regular graph, it's really clear to see that you have little growth early and fast growth at the end. That's the true pattern. And when you use a log graph, you straighten out this line, and that real pattern of growth is obscured. But another thing you can see is that you can very clearly see how many cells are there in the early hours, and you could easily add more data points at the end. So let me tell you what a log base 10 graph is. So if we go back to the normal graph, you'll notice that this is the y-axis, the vertical axis is the y-axis. You make these tick marks on the y-axis, and you decide on an interval. And the interval here is, what is this, 2 million? Yeah, 2 million. So with a normal graph, you add the same amount for each tick mark. So 0 plus 2 million is 2 million. 2 million plus 2 million is 4 million. 4 million plus 2 million is 6 million. 6 million plus 2 million is 8 million. 10 million. Each of these intervals is 2 million cells. So as you move up, you're just adding 2 million E. coli cells. That's how you're used to making graphs. With a log base 10 graph, what you're doing is you're not adding between each tick mark, you're multiplying. So you're starting with a 1 instead of a 0. 1 times 10 is 10. 10 times 10 is 100. 100 times 10 is 1,000. 1,000 times 10 is 10,000. 10,000 times 10 is 100,000, and so on and so forth. You are multiplying to get the next tick mark on the y-axis as you move up, instead of adding. Okay, and so a log scale refers to the multiplication aspect. Log base 10 means you're multiplying by 10. You could graph on a log base 2 scale, and it would basically do the same thing. It would just be more zoomed in, and you'd be multiplying by 2s instead of multiplying by 10s. It's nice to multiply by 10. You could do any log scale you wanted. You could do log base 5, where you multiply the previous tick mark by 5 to get the next tick mark. But it's just nice to work with 10s, because when you multiply by 10, all you do is, as you can see, all you do is you add a 0 to make the number bigger, right? So it's really intuitive to work with 10s. So you usually see a log base 10 graph. So what this does effectively is it makes it so that each of these intervals is a different number of cells. So the difference between 1 and 10 is 9 cells. So this interval here is just 9 cells. The difference between 10 and 100 is 90. So this interval is 90 cells. This interval is 900 cells. This interval is 9,000 cells. This interval is 90,000 cells. So the intervals start out zoomed in at only 9 cells, and as you move up the graph, you are zooming out. You are as you look up, so you can start out looking here at the bottom of the graph, and you're super zoomed in at just a few cells. And as you move up the graph, you're zooming out, zooming out, zooming out, zooming out, zooming out. And that's how you can view this, that's how you can manage this problem where you can't see anything. If you're looking at this normal graph, you can't see how many cells are there because you're in a normal scaled graph. If you want to get 18 million cells on here, you have to zoom so far out that you can't see what's going on in the first half of the day. Here, you're zoomed in on the first half of the day when the numbers are low, and you're zoomed out in the later half of the day where the numbers are high. So this gives you the ability to see the number of cells throughout the entire growth period. So in the previous graph, it looked like there were 0 cells at the 10th hour. Here you can see that there's actually about 1,000 cells. And that could be important. It depends on the bacteria you're working with, but some bacteria can cause disease with 1,000 cells. So you might want to know if there's 1,000 cells there in your Petri dish, right? So it just, this could be important data that you're totally missing the way it's visualized in this normal graph. Another benefit of this is that it's really easy to add a data point. So you remember that this E. coli, it doubles in number every hour. So at the 24th hour, you had 18 million cells. You had 18 million cells. You double that to 32 million. Well, in this graph, you'd have to double the height of the graph to fit on 32 million, but not here, because as you move up that little bit, you're also zooming out at the same time. That's why it makes it look like this line has flattened out. So all you'll do to add 1 more hour's worth of data is add a data point here. You don't have to change the height of the graph at all. You could add a couple more data points here without changing the height of the graph. So, but you could still see how much you have. Now, it's, in your homework, I'm going to ask you to estimate how many cells are present. I'll take graphs like this and I'll say how many cells are there at the 2nd hour. And you're going to have to estimate, right? Because it's hard to tell because, as I said, the scale changes as you move up. You will have to estimate. It's much easier to have accurate count with a computer. You can just estimate and feel okay about just estimating. Like if I looked at this graph and I said, how many cells are there at the 2nd hour? Well, you could say, it's something like 7 cells or 8 cells. I'm not going to be nitpicky about that. Maybe you'll say 5. That's fine. It's somewhere between 1 and 10, right? And that's fine. That's still more accurate than what you could see on this graph. You can't even see the line on this graph, right? So being able to use a log-based 10 graph to estimate the number of cells at early growth, that still gives you even though you're just estimating visually, it's still far more accurate than using this graph where the line isn't even visible at those early hours, right? Where the growth line. All right, so you will have a homework problem that helps you work with this material. And I suggest that you discuss it with your peers in lecture. Please feel free to email me if you're having problems. And I'm just going to reiterate one more time that what you have to do in terms of math to figure out how to build a log-based 10 graph, you have to use math on the axis numbers, not on the cell numbers. The cell numbers are what they are, right? I mean, you might have to double the last, if you know that there's 18 million cells at the end and the doubling time is 1 hour, how many more cells will you have in 1 hour? You'll have to double that. But in terms of the axis and displaying the data, most of the math you're going to be doing is multiplying by tens, okay? All right, so exponential growth can't go on forever, right? Exponential growth is always going to be followed by a stationary phase and then a death phase or a decline phase. And the reason is really simple. Resources run out. Every environment is limited in either space or nutrients or both. And at some point, a bacterial population will exhaust their ability to take advantage of a petri dish, of your body, or of whatever other environment they are in, okay? So let's talk about slowing of growth. Why does growth slow? Well, few, if any, resources are infinitely available in any environment. So there's limited nutrients, limited energy sources, limited space, limited water. Another reason is that waste products build up and can inhibit the bacteria that produce them. So the reason bacteria excrete waste is because they don't want it. Often waste is toxic to the individual that created that waste. Now, it's true that a different species might think that it's food, right? So one man's waste is another man's treasure sometimes. But for the species that created the waste is usually toxic. And so if as waste products accumulate in the environment, that tends to inhibit the growth of the organisms that created that waste. Okay. So if we go back to this graph here, so when you have growth, that means birth rates are outnumbering death rates. So bacteria don't have birth rates, right? So I could say birth in quotation marks, but you can say, cell production rates or division rates outnumber death rates because bacteria can also die. So bacterial division or the production of new bacteria is happening faster than bacteria are dying. And that's true in any population. You see growth when birth rates outnumber death rates. Stationary phase is when birth rates and death rates are equal. So you don't have net growth, you don't have net decline. Death is when death rates are outnumbering birth rates, or the bacteria are dying faster than they're creating new bacteria, and so you get a decline.